Hello, everyone, and welcome. It is October 25th, and it is time for, wow, believe it or not, the 179th in a row Knowledge Bolide Hangout, as always brought to you by Topher Meteorites. We are really excited today. We have a guest speaker, or actually a guest just that we're going to be able to talk to and have a conversation with. We're calling it an evening with Dr. Jeffrey Grossman. We're going to learn a little bit more about who this guy is and why we should care.
So Dr. G, or Jeff, is currently a scientist in the Planetary Science Division at NASA headquarters. And that planetary science program explores objects in our solar system to better understand its history and the distribution of life within. Dr. Jeff, now everything else he has done is...
No, don't stumble over my name. You can call me whatever you want.
Okay. Thank you, Jeff. You're so gracious. So Jeff has an impressive resume. It would take to go through all of his achievements and accomplishments, but just to name a few, he is lead scientist for asteroid materials curation. He is lead program officer for laboratory analysis of return samples. He is a program scientist on the OSIRIS-REx program. He's been part of Apollo Next Generation Sample Analysis and many more programs. He studied cosmochemistry of meteorites and the origin of the solar system and terrestrial geochemistry at Brown University and UCLA, and had his postdoc at the Jet Propulsion Lab, and then spent 25 years as a geochemist at the USGS. And he has been secretary of the Meteoritical Society, president of the Geological Society of Washington, and of course, one of my favorite things that he's done is he is the creator and editor of the Met Bull, which we all use pretty much every day. So take it away, Topher.
Wow. It makes me wonder why he's here with us today, but we're really glad he is. And sees us worthy of some of his time. So first, let me introduce myself. I'm sorry. I am Topher Spinato. I am the co-owner of Topher Meteorites, but I'm really more of a meteorite educator and community builder and content creator. I have 14 mentions in the Met Bull, and this is like one of my pride moments here at the Busick Center for Meteorite Studies, holding Murchison, right after being told there's probably a Nobel Prize hiding in that jar. So really interesting thing. And one of the things I like doing is I like spending my time, when possible, sharing with kids the information that we have and making videos. We're actually going to make a new video series for kids, and hopefully we'll be inspiring the next generation of science leaders by doing that. Currently on the Knowledge Bolide channel on YouTube, there's well, you see the stats right there online, that we have 12,000 subscribers, and there's a lot of people who don't subscribe that check in and watch. So we're really a leader in the education of meteorites. So my question to you, to kind of kick things off, is I'd like to get to know a little bit about you. Whatever you're willing to share. Married, kids, favorite movie, favorite vacation, favorite band. What are you into? Contact football, or is there someone that you look up to that you would like to call out, or perhaps the wildest claim ever made about a rock as someone submitted to you?
Oh, well, that last one is easy. It was when I was a grad student at UCLA. We got meteorons sent to us all the time. We got some really good ones. One was if you put it near a cactus, the cactus would bend over back and forth, therefore it was extraterrestrial. So that was a good one. And the other one was a citrine crystal from the planet Skylar, which they wanted us to analyze. So I've gotten some pretty good ones. I'm sure anybody out there, and I know there's people here that take meteorons, would have much better stories than that to share. But let's see, about me, I am married. I have one child who's over 30. I've been working on meteorites since 1977 when I went to UCLA as a grad student. with John Wasson, who was my advisor there. Been sort of working on that and related topics ever since my whole career. There's a lot of things like you asked, but let's see. Hockey is my sport. Like that, follow the Caps. Before that was the Rangers because I'm from New York, but now it's the Caps. I probably see there's a clarinet back there. I played clarinet in all through grad school. I haven't done it much except dabbling recently. And I don't collect meteorites. I keep my hands clean so that when I sit in judgment of meteorite names, I don't have any conflicts of interest. So I don't own a single meteorite. Although I think my wife has a pendant with a piece of like Gibeon on it. So maybe that's the exception. What else would you like to know?
We're going to save something for your second and third and fourth visit. But it was, it's so weird because we were looking for information about you online, and I was joking with my wife that she got the wrong picture of the wrong doctor because there's not that much information about you. But yeah, so I'm glad that you shared what you did. It makes us feel like we know you a little bit more. Our first knowledge bolide crew member that has a question for you is going to be Carl. So let me get Carl's camera set up, please. Go for it. You can introduce yourself if you don't mind, please.
Sure. Well, hi, Jeff. My name is Carl Patzer. I live in Ithaca, New York, the home of Cornell University. I have been collecting meteorites for over 30 years. I've had a deep interest in astronomy and mineralogy since my youth. Even though my collegiate studies were in history, I took quite a few astronomy electives while in college. I do consider myself an accomplished amateur in both fields. And I do quite a bit of public outreach along with my wife at schools, museums, planetariums, and have so for the last 15, 20 years. I would like to know what initially ignited your interest and what has since become your field of expertise.
Same as you. So when I was in college, I was really interested in astronomy. I like making lists, and I made flashcards of the constellations, some of which only had 3 dots on them. And I memorized them and then learned all the constellations. And then I went to college and ended up being almost a TA of the introductory astronomy class, which I had never taken. But I was majoring in chemistry, and it was the marriage of astronomy, which I loved, and chemistry, which is what I was doing. And it led me into cosmochemistry. And so I tried to find a way forward that would wed those. And so that led me to apply to graduate schools, which I didn't even know what they were. Looking up the word cosmochemistry, applied to 5, got into a couple of them, and went to UCLA.
Oh, very good.
Well, that's how it works. Exactly the same story you have, it sounds like.
Well, thanks. I'm so glad you could join us this evening.
Except the number of meteorites in collection.
Yeah.
Well, we went different directions, right?
Yeah. We have Jeff DeVries joining us from Canada. Jeff, you have a question, or can you introduce yourself, please?
You betcha. Hey, Jeff, it's Jeff here. I'm an electronics engineering technologist. I definitely have a strong interest, again, started off in astronomy and kind of amalgamated into meteorite collecting. For me, what's really important with meteorite collecting is the provenance, the past story. So it's not just only the science aspect of things, but also the human factor, the historical aspect of how a meteorite goes through different hands and the history behind that. And one of the really cool things that I've gotten into recently is I've been working with a fellow by the name of Michael Mazer, who is one of the main mass holders and finders of meteorite by the name of Moss. And he's at the University of Western Ontario.
I classified Moss.
Perfect. So yeah, so you know who Michael is because he's in the bedpool there. But he's been working with me and at Ingleton Observatory. If you want to go to the next slide, Topher, he's built a all-sky meteor camera for my observatory here in Alberta, and I'm actually just working with him setting this up here hopefully up onto the observatory this weekend. So to be able to track trajectories and whatnot. So kind of taking the science to a different aspect besides the classification piece and whatnot. But the next steps with this system is putting on spectroscopy cameras as well. So do a little bit of spectroscopy as the meteors go through the sky and hopefully capture something that hits the ground here around Alberta. So so I guess my question is for yourself is out of all the amazing projects and initiatives that you've been a part of or pioneered over the years, what are you most proud of so far?
Thank you for the so far, because I am late in my career, but there have been several things which I'm pretty proud of that probably relate best to this group. One was around 1980, I worked with Derek Ceres and a few other people at UCLA because we were noticing that not all type 3 ordinary chondrites or any type 3 chondrites, they were not all the same. And so we started putting together the properties of them and discovered that they showed as big a range in metamorphism as the type 3s through 6s did. And so that subclassification of type 3 has stood the test of time now. That was published in 1980, so that's a long time. So that I'm very proud that is. And then later in my career, I subdivided those type 3s into you've seen 3.00, 3.05, and it was the same thing, that the metamorphism is a kind of logarithmic process. And so there was a lot of variation in just the low parts of the group. And these things have stuck around and are still used. So I'm pretty proud of those. And then, of course, being part of OSIRIS-REx at NASA, I joined OSIRIS-REx as the program scientist the year that it was selected, which was 2011, and I've been with it ever since. And you're just beginning to hear results from it. And I can't share with you any unpublished results from it because that'll all come out in the normal publication process. But that's it. I'm very proud to have been a part of that all as well. So it's been a long arc of cool things to be involved with. And I'm proud of the Meteoritical Bulletin too. I never expected this to become what it is. So that's neat. I'd like to make sure it has a future too, and working on that right now.
Very cool. Thank you, Jeff.
All three of those subjects are addressed in questions later on. So I'm glad that those are things you're proud of because you're going to get a chance to address them individually later on. We have a little segment about sample recovery and your involvement with that. So coming up next is Allison. Allison from Montana. Are you with us?
I am. Hello, Jeff.
Hello.
I am Allison. I'm a meteorite hunter, a rock hounding and lapidary content creator, and a meteorite jewelry designer. I have a small family, me and my 2 boys up here in Montana, and we're very enthusiastic about being outdoors and have incorporated meteorite hunting into our outdoor hobbies. My question to you this evening, there we go.
Sorry.
That's okay, thanks. You've had a very long and successful career. How have things changed over the years? For example, have advances in fields such as computer technology made the sharing of information and made data collecting and processing of samples faster and easier?
To say the least. When I started at UCLA, that was 1977, I got on a computer there and typed help. And it gave me a list of commands it can do. And one of them was telnet. And I typed telnet and it said, example, telnet Stanford. And so I typed that and it said, welcome to the Stanford Computing Center. And I almost fell out of my chair. So that was the internet in 1977. It was, I guess it was still ARPANET and UCLA was part of it. So meteorite information was in books, the catalog of meteorites. Many of you probably can rattle off all the editions that there have been of that. You had to wait for the next one to be published. What was it, every 15 years, 20 years, something like that? The Meteoritical Bulletin would be published at first in Russian, and that would announce new meteorites maybe once or twice a year. I think in the early days it might have been more, but information did not flow well. So time went slowly and you had to wait for things. And a lot of people knew things that nobody else knew because information did not spread. So things have changed enormously. And then there's, I mean, that's just computing. So when I started putting the bulletin together, there was no computerized catalog of meteorites. It was we were doing it with Excel version 2.1 or something.
Oh my goodness.
Yeah, and so we wanted to have something that could be. I wanted to have something that I could share, and so I learned to code myself, and it's primitive, but things have changed a lot since then, and I think the next generation of the bulletin and everything else has to come out. But everything's, and then analytical capabilities. We processed microprobe data, which is used for meteorite classification. When I came online, punch cards were generated from your microprobe, which you would read Nixie tubes and write down the numbers and type them in and make punch cards and put them into the mainframe computer in the computing center to do the corrections, and that was your probe data, which you would then type in to a table and publish. So
Wow.
I think things have changed just a wee bit since then.
Yeah, definitely. Made your job a lot faster and easier. I think it's fascinating too that we're even able to do this. We're able to get together on a Zoom meeting with like-minded individuals. So thank you. That was fascinating.
Awesome. Thank you. I'm going to talk a little bit. I have a question that I want to ask a little bit about classifiers and what the future looks like to you. So in my limited years of meteoritics, I've been very, very fortunate to be invited to 3 of my heroes' facilities, Dr. Garvey, Dr. Irving, and Dr. Ajit. Obviously, I'd love to add Dr. Lubin and Dr. Chris Hurd to that list, as well as yourself. But my question relates to, like, there's not very many places and people classifying meteorites. And when you consider the institutionalized expenses for the diagnostic equipment, the ongoing curation of samples, and what a student has to go through, the lengthy education and expensive education, I'm just surprised. There seems to be a need. I have a perception that there's a need for more classifiers, especially younger ones, like we have Daniel Shake joining us today. Do you kind of see the classifier scientist pipeline half full or half empty, or what's your thoughts on that?
Well, I mean, I don't think it's ever been a very big pipe. It takes a special kind of person to get into that. It's the kind of person who likes to make discoveries of new things and can go in many different directions in their career, and that's the way they like to do research. And it's just a certain kind of person that ends up doing this. You might want to direct that question at Daniel and find out what he finds fascinating about it. But it's never been a big pipeline, and it's the necessary one, because it's not just collectors that want to see their meteorites classified. Scientists need to know what they are too. So, but there's not all scientists work that way. And especially if you're interested in missions and things like that, you're thinking about science in a very different way. So I don't know what the answer to that is, other than new generations of classifiers have come along as the older ones retire. So I hope it continues, but I don't really have that much insight into whether it's dying or expanding or whether there's a problem. It's never been a lot of people doing it.
Yeah. Wow. Well, I hope that programs like this and interviews can continue to get people interested in it and bring new people on board, because it's a science that I think would be in super high demand. We have to wait for our classifications, and a lot of the scientists will only work on planetary stuff. So I'm interested to see how that plays out myself. We have Jim with us. He's a Missouri guy. So, Jim, are you online?
Yes, I am. I'm here in Independence, Missouri, and because I'm in Missouri, way back when I decided to start collecting Missouri meteorites. My degree is in physics, but I worked my entire career as an electrical engineer, and I'm retired now. And because there are so few Missouri meteorites, as you can see in the case here, that whole front section is Missouri. There are 18 Missouri in the case, and there's 24 to be found. So I'm still short 6. And I only can find about 1 a year to fill out those missing 6. So I started collecting other named meteorites. And I've got 3 of these cases like this now, full of my collection. I give them away to students, to guys at the rock club, to rock shows around as outreach. And so far, I think I've got 3 or 4 people that are starting to collect meteorites just based on me passing some out. I do have a question for you, Dr. G. I've noticed in the Met Bull that there are some detailed entries in the Met Bull, but not so many in some others. And I was wondering what information the non-com receives from the classifier. In addition to the chemistry, does the non-com receive all the history, the graphs, and the photos that the classifier uses?
Not really. But before I answer that question, I see half the meteorites in Missouri are irons, because you live in Farrington Circle, one of my favorite things. But that's a subject of another day.
The ones that I'm missing are irons from the 1800s.
Yep. And that's a wonderful topic to speculate about, as to why there are so many irons in the southeast U.S. all the way out to you. Back to the Meteoritical Bulletin. So most of what you see in the bulletin is most of what we have received. We do occasionally, especially for sticky ones, where the classification is complicated. We sometimes do get a few charts, or we might ask for more information of one type or another that is not published. Occasionally, a submitter says, here's a picture for you all, but I'd rather you didn't publish it. But those are the exceptions. Most of what you see is what we used to classify it. So there isn't a lot more. And I've edited every single write-up in the Meteoritical Bulletin, all of them. And I will edit out extraneous stuff and condense sometimes, but it will be things that don't add to the classification, and it's not much. So what you see is what we got.
Okay.
The reason some meteorites have more information than others is because some meteorites are more routine than others. So ordinary chondrites, equilibrated ordinary chondrites especially, we really don't need much. We need to know that you know how to classify meteorites. So you have to have shown that you know what you're doing through experience. And we need basic information like silicate compositions. Often we'll see a magnetic susceptibility measurement. There are various basic things that let you classify it, and then we will accept that. If you know what you're doing and you did the basics, that's enough. And there won't be a write-up. There'll just be the numbers that you see in tables. And the more complicated the classification is, the more you tend to see. So there are exceptions to that too. For example, if you have a meteorite that's clearly paired with one that has a long description and it's found in the same region, you really don't have to say that much basic data, and then it's paired with the other one. It looks exactly the same, and that'll be enough as long as we know it's been studied enough to establish that pairing. So, there's variation, but it depends on how hard it is to classify meteorites of that group and other factors like I just said. So, and of course, some meteorites are just exciting to the person classifying them, and sometimes it's an ordinary chondrite. Sometimes somebody writes 5 paragraphs about just an H5 find from Nebraska, and we'll publish it. If they want to do the work, we're happy to put it in. So,
okay.
And we love reading the stories too when there's some in there.
Yeah.
So yeah,
the stories are part of the magic.
Yeah.
Yeah.
And it's disappointing when there isn't a story. Like for most of the Northwest African meteorites,
Yeah.
there obviously was a story behind a lot of those, and you just don't hear it. It just gets sold and changes hands a bunch of times, and then you never know.
That's a shame, and that's one of my wife's thorns in her sides when she's doing her Met Bull stuff. So that's a good segue to Sue.
Well, I'm going to reintroduce myself. I'm Sue. I'm Topher's wife, and to help run Topher Spin Meteorites with him. And he creates most of the educational content. But I make content too. I usually direct it at a younger audience and try to make meteorites appear to be as cool to them as they are to us, because I want to get like the teenagers involved and things of that nature. And you've already answered some of my questions about the Met Bull, but the Met Bull for me was really significant because when I started getting into meteorites, that's actually where I got a lot of my knowledge and learned, going down the rabbit hole, looking up, a meteorite, and then, oh my gosh, Topher, look, you can pull up a list of all the other, K1 meteorites, and I've used it. So I've read the Met Bull for hours, and the first serious content I started making were Met Bull updates, and then went from there to some meteorite trivia games and things of that nature. Now, my question was about the birth of the Met Bull. You answered a little bit about that, but we were all wondering, did he have any idea how significant this database was going to be? And I don't want to sound like I'm going crazy, but a lot of us consider it to be our Bible because we refer to it every day. But I mean, Did you really have any idea it was going to be as big as it got?
No. Part of the birth of this was my good friend Monica Grady, who published the last catalog of meteorites out of the UK. And it was talking with her a lot. It's like, when are you going to update it? When are you going to update it? Are you going to update it? We're getting behind as more that was published in 2000, which is like right at the beginning of when Northwest Africa's and a lot of other desert regions came online. And so the numbers of meteorites were going up really fast. They weren't in the catalog. You could buy, I think MetBase existed right around then, and you could buy that. It was commercial. And so, it cost a significant amount of money to get that. So I wanted there to be a way to update the catalog of meteorites online so that it would bridge editions of the catalog. And then the catalog stopped coming out. It hasn't been a new one for over 20 years now. And I don't know if they're planning on doing another one. I think times have changed. And I think they're happy to have it be published this way, but I won't speak for the people in London. So instead of bridging, it just turned into the whole thing. And I got permission to get a lot of supplemental data out of the catalog, not their text. But then it just took off. And once it got established, there's far more meteorites that have been found since 2000 than before 2000. So now it's the problem is reversed. If anybody ever wanted to publish a book, I don't think they would. But now it's them would have to do most of the catching up, and it would be tough. And I don't know that it would be valuable.
I don't know how many trees you'd have to chop down to print what you have actually compiled. So that's amazing. Thank you so much.
It's a lot. I mean, there've been so many meteorites, and the last few years have been the biggest years ever. I mean, there's a lot of meteorites.
When we run the reports to do the updates, I'm always astounded at how many meteorites have been classified.
Yeah, I'm going to jump in with a tiny bit of a selfish question, but I want to get this information so I can share with other people. Can you take a look at these meteorite classification charts? Just give me your opinion on them. If you know where we can get better information, what can we focus on these? What can we learn from? Just your initial impressions. You might be familiar with these. This one is the one we kind of used during our Meteorite 101, where we went down all the classifications. And then this is another good one, but we don't use that much.
I like that one better.
Okay.
I'm all about the images. So I guess I could review it for you. There's a lot of information on that chart, and and I looked at it briefly, and I can take issue with some of it, but it's competent, and so I guess what I'm saying is if you'd like me to review it, I'd be glad to, and try to find things that maybe not so right. For example, go back one to the previous one. For instance, the increasing temperature there, that's not strictly speaking correct. I mean, it's overall right, but it's not as you present it, because there are cooked up chondrites, and there are, it's not that simple. And they're all different temperatures on the left. So there's going to be things that I'd quibble with. But I'd have to look at this really closely, and if you'd like, I will. There's some groups on here that aren't well recognized as being official meteorite groups. I remember the good old F chondrites when those came out. It's just one abstract.
Yeah.
So there's some things on here that aren't widely used.
I think one time would be really nice to have a conversation just about like the chart. That would be an entire evening. I would appreciate if you have any other collateral like this that you can share with us, or if we can, well, Sue and I will get with you offline. But yeah, I do like this one, just so we kind of know what we're looking for when we get in there a little bit more. So
I
yeah, that'd be awesome.
love this. I love this.
Okay, good.
I've never seen one like this before, and you could carry it further with mineralogy somehow if you could do it graphically. I don't know, but this to me is like, what do I have? And you can look at this and see the textures. Now I haven't looked carefully to see, some of these things have very highly variable textures, so maybe one image isn't so great, but
Yeah.
this is pretty cool. I like it.
And this is
Somebody-
courtesy of Matt Genji. So I did not make this. I claim no stake to it, other than I use it to propagate knowledge. So
Yeah, I like it.
oh, good. I appreciate that.
And Daniel made a comment in the chat too, that the lunar classifications could be expanded on that. So I think one of those charts came from 2021. So it shows you how many meteorites have already been classified in the last few years.
Yeah, in fact, the HEDs could be expanded, the Uralites could be expanded. A lot of these things have lots of subclassifications and different types and textures. So you could expand a lot of these things.
Yeah. Wow. That's a project for another day, but we're very interested in any help you can offer. Thank you very much. We're gonna shift to a question from one of our crew members that his name is probably very familiar with you. You've probably seen Matt Stream as the main mass holder or submitter of many samples. So we have Matt Stream with us.
Welcome, Jeff, and welcome to the Hangout and everybody else. My name is Matthew Stream, and I have a bachelor in environmental science with emphasis in geology, and I studied at NAU. I worked a little bit with Dr. Jim Whitkey, who is very familiar with the Meteoritical Bulletin, and he's classified many meteorites. And so attending that university, I began collecting meteorites and being obsessed with them. And so now I have about 83 mentions and a few pending in the Meteoritical Bulletin. So that's kind of what got me into it, was not only that, but I'm a hunter, I'm a collector, and just enthusiast. So I guess just getting outdoors and being in science is what led me to loving meteorites. And these are just pictures of us hunting. Topher was there in Franconia.
Yeah. Yeah. Now I think you have you have two questions about carbonaceous stuff that, so I'm going to put both of the questions on the screen and then I'll slip through some pictures and whatnot. So go for it, Matt.
Okay, cool. Yeah, the first question is kind of broad. I apologize, but I'm really excited about the new samples and glad that you were able to work on that. That's really exciting. I'm just kind of wondering what the difference is in C2 and C3 carbonaceous. I guess for easy beginners to understand.
So let me ask you to clarify this. You mean when they appear without a CM or a CO?
Yeah.
Is that what you're asking? Or just in general, what's the difference between those types?
Without the CM and all that stuff, yeah.
Yeah, so the evolution of classification of chondrites and carbonaceous chondrites in particular was way back, late 50s, early 60s. There were these Roman numeral classifications, C1, C2, like that, they were really looking at the difference in degree of hydration of these things, where C2s were quite hydrated, C3s were not, and C1s, of course, we didn't have many silicates left, any anhydrous silicates left. So the numbers in carbonaceous chondrites are different than what you find in ordinary chondrites, which is 3, 4, 5, 6, because here it was talking about hydration, and in ordinary chondrites it was talking about metamorphism. Now, of course, we now know there's some carbonaceous chondrite groups that are type 4, 5, and 6, like CKs and some others. So carbonaceous chondrites now use both schemes. But when you see C2, it means one of two things, and probably one thing. It hasn't been put in a group. The groups are chemical groups. So CM, CO, CV, CI, CK, those are chemical groups. They're meteorites that all share a very similar composition for certain kinds of elements. There's some differences for volatile elements for some of them, but in general, they're a chemical group of closely related meteorites that may come from one parent body or one group of parent bodies that are similar to each other. So that's what the M, O, V, and K are. The two and 1, 2, and 3 in carbonaceous chondrites is generally the old how hydrated is it, because we still maintain that old scheme. It's not in a different parameter. So when you see C2, it probably means nobody has ever tried to classify it. Like it's very small, or it's an old specimen that hasn't been looked at by a modern scientist. Sometimes, so either it's hard to classify or it hasn't been classified in a very long time. That's what it usually means. And same with C3. So somebody looked at it and said, it's not hydrated, it's got lots of chondrules in it, and we don't see the phyllosilicates, or based on the old evidence, we don't think it has those things. So it's C3, but they don't know much more about it. Nobody's ever really looked at it. Usually nowadays, if it's can't be put in one of the groups, it'll say something like C3-ungrouped. That means it's type 3, not very hydrated, but it can't be easily put in CM, CO, CV, CK, etc. So that's what, and if it just says C, that means nobody has ever really had a good look at it, usually.
Okay.
It's usually old things that are grandfathered or grandparented, maybe I should say, into the bulletin from older literature.
Could you
and there are things.
I'm sorry. Could you perhaps slide this new classification into your discussion? This Hasi Kabeb, however I'm supposed to. It's C3, and we have some pictures and then the isotope test.
Yeah. So I mean, C3 ungrouped means somebody tried to fit it into the known groups and decided it didn't fit. It had enough properties that were different that they could not assign it to one of the groups. So either the group is more varied than we know, or there's a new group lurking out there that this is a member of, and we don't know which of those things it is.
Oh,
And oxygen isotopes, this is an oxygen isotope diagram, of course, and the X's are that meteorite. And it's showing you where it plots in 3 oxygen isotope space. I could explain a little more about what those diagrams mean if you want, but basically this is used as a map of meteorite space. Meteorites that are related to each other plot either in one place or along a simple array. Arrays that are like those red dots representing the CVCK or mixing lines. And things that are on a slope 1 line, like what TFL is terrestrial fractionation line. Everything on Earth would be on that line, and that's a mass fractionation line. That's what isotopes like to do. They like to separate based on how heavy they are in nature. And so everything, and they do it, their masses don't change, so everything does it the same way on Earth, and things stretch out along a slope 1/2 array. So that's how we fingerprint meteorites. You can see some things, some groups have a wide range. And those orange X's representing this point, they don't fit well into any of the groups that were on this chart. There are some other groups that are not on this chart. There's also some lone meteorites they could be possibly matched with. But that was one piece of evidence, as I recall, for this meteorite, that it didn't belong to any of the normal carbonaceous chondrite groups.
very cool. Thank you for explaining that.
And here's another name you may be somewhat familiar with. Is Roberto Vargas with us?
Roberto, I just heard back from him. He is stuck in traffic right now, trying to get back from the airport. He was trying as hard as he could, and he just couldn't make it.
I'll go ahead and do the intro and try to ask his questions on his behalf. Roberto Vargas is a meteorite dealer and hunter, very successful hunter. He's the president of the IMCA as well, and actually a good friend of the Knowledge Bolide. He's on here quite often. Here's some pictures of him on the left-hand side collecting the hammerstone from Muskogee that hit a barn roof. And there's, I think, Junction City on the right-hand side.
I think that's Cranfield.
Cranfield, okay.
Yeah.
Sorry. So the question on the screen, you can read it yourself, is oh yeah, we knew a question about groups and grouplets was coming up, so this is one of them. If you could address this.
Yeah, so it's a good question. I guess what you have to know about the Meteorite Nomenclature Committee, which is who publishes the Met Bull. And I'm a member of that committee as editor of the Met Bull. It's conservative. We don't want to be pushing the science ourselves or driving the science. We want to be following the science of meteorite classification. We want to do it conservatively, and we want to put things into the bulletin when we're confident that the community has accepted this classification scheme. And so slowly, new classification schemes and new subclassifications or whatever they are make their way into the bulletin. And the discussion that will be had on the Nomenclature Committee is, what is the evidence for this? Are we seeing it used in scientific papers? Are others grabbing onto it? And if so, and if it meets conservative tests for the way groups should be formulated, then we'll do it. You know, carbonaceous chondrites traditionally all start with C. CT, CZ would be acceptable carbonaceous chondrite names. The question is, like, have those things caught on among scientists? Are they being used? And has the basic element of a meteorite group been established? Do we know that they're compositionally related? Because these are chemical groups, the carbonaceous chondrite groups. So, you know, we'll look at all those things, and when they get established, we'll start using it. There'll be a vote, and we'll say, should we use it? And we vote, and if the vote passes, then we'll start doing it. I don't want to really talk about K chondrites because that is a little bit buried in history. Yeah, there's one from 2013, but the Nomenclature Committee really never played much of a role in deciding whether that was a group. It's kind of grandparented. So yeah, there's really not very many of them. We like there to be 5. John Wasson is the one that created the rule of 5. It's not a formal principle of anybody. It's just a tradition in meteoritics. And it's nice when you somewhere in your life you establish a tradition that's still followed. And 5 is the tradition. So do you need 5? No, but we usually like there to be, and that's what the community kind of expects. Did that make any sense?
Yeah,
I mean,
absolutely.
it's just a conservative advancement of classification science.
It's a never-ending desire to, well, classify things into different categories and fine-tune that over the ages. And we, every once in a while, we get overwhelmed. We see so many ungrouped that we're like, well, there's got to be 5 in there by now. So yeah, I didn't mean to throw the K's at you, but there's so little weight that we don't have to worry about collecting it. So don't worry about it. We are going to switch gears to the OSIRIS-REx, and in the opening introduction to you, 2 of the things that you're a participating scientist in the Hayabusa 2 and also in the OSIRIS-REx program and the next gen Apollo, just amazing stuff. So that's kind of where the conversation is going to flow now with Scott McGregor asking a question.
Hey, Jeff, thanks for joining us. I'm a collector of meteorites, and I especially like carbonaceous chondrites and particularly fond of bencobonates. I'm also a sponsor of an effort with the B612 Foundation to try and find new asteroids out there and analyze those. And so hopefully they'll be getting up to thousands of asteroids of additional discovery pretty soon. Question for you. Perhaps you can describe some of the various tests and procedures that you're going to be using to analyze the makeup, chemical makeup and structure of the Bennu samples, and beyond what you would do for just normal meteorite classification. I'm sure there's a lot of interest here, and I can imagine you also had a fair amount of debate about destructive testing versus non-destructive testing, how many samples you need to reserve for the future, and so forth. Would love to get some insight on that sort of process. And then, of course, if you have any hunches on the likely classification and what it might be most similar to of meteorites we know.
I really can't, on that last question, go beyond what has been put out in our press releases. And so what you know so far is it's very dark and it's very rich in water and carbon. There's also, there's a few other pieces of information in there. It has sulfides in it, but I can't go beyond that because the scientific process is playing out, and we don't spread rumors. We wait for for the work to be done, and then we make an announcement. So I'm sorry I can't give you any more insider information on what it is, but you certainly can start guessing and see if you're right.
But fair enough. But what are you going to do to figure it out? What kind of tests are you going to run, and any unusual ones?
Occasionally, a really interesting meteorite falls, usually as a shower, usually a carbonaceous chondrite or something like that, and it'll quickly get snapped up by scientists who form a consortium because there's a lot to learn about it, and it's more than any one person can do. A single classifier can collaborate, usually has a network of collaborators, but it's limited in what they do. They maybe have an oxygen isotope collaborator. They maybe have, somebody who does some kind of analysis of the organics, usually spectrally or something like, or magnetic susceptibility, but they're a small project. And so they get enough information with the critical techniques to classify it. They may launch a whole career of studying it themselves, but sometimes these consortia meteorites come up. Sutter's Mill was one. Tagish Lake spun up some consortia. And these are bigger groups that are taking an interesting meteorite. They usually form organically. The groups do. where scientists interest each other, and or there's just interest that coalesces into a big consortium study, and more techniques are put to it. Now, the return of samples in OSIRIS-REx. OSIRIS-REx is $1 billion mission. It's a New Frontiers mission at NASA, and that's the size of its budget. It's a big project, and so we have put together a New Frontiers class sample analysis team. This is bringing world-class people in all the areas of science needed to answer the wide range of scientific questions that OSIRIS-REx is answering. So the project itself has people, it's over 200 people. They come from many countries, and I think that the list of methods being employed is very large, maybe 75 or 80 different analytical methods, including most of the cutting edge methods that you can imagine. So it's a world-class project with a world-class consortium. The project team is essentially a consortium being driven toward answering very well-defined goals, and discovering whatever else is going to be discovered along the way, of course, because they are not going to turn their nose up at knowledge. So it's just the scale of project that's very different than almost anything that happens with meteorites. The Hayabusa 2 mission returned a few grams of sample from another carbonaceous asteroid, and they had also put together, a world-class team of people to study it. So this is big science, as opposed to what normally happens with meteorite science, which is a much smaller scale. It's very cool to see it work.
Yeah, fantastic. Really appreciate it. Our next question is from Mike, and I just want to point out that in the year and a half that we went through our Meteorite 101 series, focusing on different classification every week, and sometimes multiple weeks for carbonaceous. Mike Kelly is our instructor for that. He put together most of the slide decks, and we rely on him highly here on this channel. So Mike, are you with us?
Certainly am. Thanks for the intro, Topher. Yeah, so I'm Mike. I'm from Stroudsburg, Pennsylvania. Got an undergrad in geology, so I love field work. So I like meteorite hunting. I also like writing articles for Met Times. So that's me in a nutshell. Basically, new thing I'm getting into and love doing is making thin sections from meteorites. And so I wanted to talk a little bit, since we're on the OSIRIS-REx part, of how curation has kind of changed since the original Apollo samples have come back, and what we're doing kind of a little differently with the OSIRIS-REx stuff now, and then where we're going in the future, right? Because we've got the rover going around on Mars, currently picking up samples, getting them prepped for a future return mission, and we're also looking at future missions to the moon. So where kind of is curation going, and curation techniques and curation procedures for future return samples?
Yeah, that's a really interesting question. I mean, we're not going back to the Apollo days. You'd be surprised how sophisticated they were. They were worried that there might be life in the lunar samples. So, the original Apollo protocols were much more severe than they later realized that they had to do. But they have followed basic curation principles since then. The principles haven't changed. You want to keep the samples isolated from the terrestrial environment, so that when you study the sample, you're studying the moon in the case of Apollo. You're not studying Earth. We've just gotten a lot better at doing it, at understanding what kinds of materials in a curation facility can contaminate a sample. When the Apollo days, we didn't have any idea the kinds of organic analyses that would be done on these samples in the future. And so some of the compounds that you would put in your curation chamber turned out to be contaminating some of the samples. We learn these things as we go along. We learn what materials to use. We learn the conditions to keep them in. We learn how to handle them better, what our tools can be. And we're always learning from the lessons of failures or problems that happened before us. And so we build and build and build, and things the principles are basically the same, but we're doing things just much better and with much better knowledge. And so when somebody gets an OSIRIS-REx specimen, they can be confident that they're studying the asteroid. They're not studying themselves or the burger somebody else ate that was curating it, or whatever. Now we're going in some new directions that are going to require change in creation. As we explore the moon and the Artemis program progresses, at first we're going to return samples that are ambient conditions, but eventually we hope to go to the lunar South Pole and start returning samples that are collected cold and returned cold, or even at cryogenic conditions, which are really cold. Those will have to be brought back. We have to figure out how to do that. We have to figure out how to curate them. We have to figure out how to handle them and allocate them, and the science community has to figure out how to study them. These are all the next generation of challenges. And of course, if we do a comet sample return in the future, we'll have to do the same thing. Mars sample return is a whole new set of problems, because we again are going to have to worry about life. The Mars samples have to be protected in two directions. We have to make sure that the samples don't contaminate us and we don't contaminate the samples when they're brought back. If we don't know if there's any life on Mars, we don't want them contaminating life on Earth. And if we're trying to figure out if there's life on Mars, we don't want Earth life contaminating them. So that's a whole new set of challenges on how to curate and handle samples, is how to do that double protection. So that's where we're going, cold and back to worrying about biosafety. So those are the big challenges, and those are going to be very difficult things to overcome and do, but they're doable.
Super
Thanks.
exciting.
That was incredibly insightful.
Yeah, I agree. We have Mike. I'm sorry, we have Cliff up next. Cliff has a complex questions. It's asked over 3 slides, so I can click back and forth through them, but I want to make it easy on everyone. Cliff, are you with us?
I am. So
Thanks.
the first part of this, it has to do with the OSIRIS-REx Bennu sample obviously was surface sampling in the sense that it was a simple touch and grab from the surface of the body itself. Is there any expectation that there will be solar wind effects that would have changed any aspect of the surface, or from that particular location, is it expected that it will be relatively pristine?
No, space weathering is a process that we know affects planetary bodies, airless bodies in particular, and like Bennu. So space weathering is something we expect to have affected Bennu samples, and one of the goals of the mission is to study it.
Okay.
So in order to, it is a surface return, but you may know that the tag SAM, when it came down, it kind of didn't feel much resistance from that surface. It touched and it kept going, and it went about a half a meter down before we fired our thrusters and backed away. No telling what would have happened to the spacecraft if we didn't do that. So it did collect samples that were not right on the surface, but we put these contact pads on the bottom of OSIRIS-REx's collector. They're basically Velcro-like pads, a metal Velcro, 24 of these things in a ring. And the idea here was, as soon as it touched, then very, very surface grains would get embedded up in those collectors.
Okay, that gives you a control reference.
Well, it's particles that we would hope came from the extreme surface that were actually exposed to space weathering right at the moment that we collected it. And of course, asteroids churn and the material gets overturned, and there can be past space weathering even on things that are not on the surface. But we did that experiment in order to study it, and that's one of the goals of the mission. So we expect it, and we're going to be looking at what the effect was and learning from that.
Okay, excellent. Along those similar lines, is Bennu expected to have aggregate surface material from other parent bodies that would have been, gravitationally collected over time, or do we not know enough about its environment to be able to say with any certainty?
Well, what we don't know certainly outweighs what we do know. That's why we explore space. the team found evidence that there was foreign material that didn't seem to be related to a carbonaceous asteroid. When we explored it with remote sensing, there were these very light-colored boulders that the team hypothesized might actually be HED-like, coming from Vesta, pyroxene-rich things. It's remote sensing data. It's got value, but nothing is more valuable than getting it into the lab and finding out exactly what it is. The team will be looking for things like that in the sample, and so we'll see. But yeah, I mean, this asteroid is a rubble pile. It's been broken up through some collisional process and reassembled into the body it is now, much smaller than the parent body. So there have been impacts that caused catastrophic changes in these asteroids. There's craters on the asteroids. Other stuff's always moving around in the solar system. A lot of these are not constructive, but some, the material just flies away, but especially with the body as small as it is now. But some of these things, some parts of the impactor can probably hang around in some cases. So we don't know what we're going to find. And we also don't fully understand how these bodies assembled, or exactly where. There's evidence that some asteroids or small bodies in the solar system were being shoved around by the giant planets like Jupiter as they changed in their orbits. That sends things careening around and mixing, and we don't really know how these processes work all that well, and we're hoping to learn more. So we'll see. We think there's two kinds of boulders on Bennu from the remote sensing. Does that mean they're from two different asteroids, or is it two different parts of the parent asteroid? Or we don't know yet. We're hoping to learn all this, so it'll be cool to see what comes out of it.
Okay. Then the last part was this is more a theory question. Since it's not something I have much background in. A small carbonaceous body like Bennu obviously is I wouldn't expect intuitively to have any kind of enough separation to form layers the way that, say, iron cores form in larger bodies. But I was curious whether or not there would be enough gravitational force, at least in theory, on such bodies to concentrate toward the core and maybe squeeze or heat water out of the parent minerals. Do you know if there's any theory on that?
Well, I mean, it depends on a whole bunch of factors. First of all, Bennu is not an asteroid. That existed as it originally formed. It's a rubble pile. It's a secondary asteroid of some kind. So whether it came from a 100-kilometer body or something like that, it seems likely. So it came from a bigger asteroid. When we look at carbonaceous chondrites, most of them don't have clasts of metamorphosed versions of themselves in them. A few do, but most of them don't. And you'd expect if asteroids were being disrupted and reassembled, you'd probably get a cross-section of material from that body. Not in every case, but the fact that it's almost no cases, say in CM chondrites, makes me think that it's unlikely that that body ever fully differentiated. And that can be because of where it formed, that it could have been an icy body, or when it formed, was it big enough to keep in heat from the decay of aluminum-26 and other elements like that? Or when did it form? If aluminum-26 is a heat source, which it might be, if you form too late, you've decayed away too much of the aluminum-26. So time and space and the history, all of these play a role. I suspect, well, we don't know what Bennu is yet because they haven't done the analyses, but I suspect we will find little evidence that it differentiated with a core. There are other kinds of differentiation that one can speculate about involving water and ice that are kind of cool to think about, but there's nothing coming out of this project yet that is at the level where we could start making any kind of speculation about that. So it's just me thinking about what one might learn.
Fair enough. That's exactly what I asked for. So thank you very much. Appreciate it.
Staying in outer space, we have Bruce. Bruce, are you with us?
Yeah, I am. So thank you, Jeff, for coming and joining us. I'm a child of the Apollo lunar landing eras, and I've had a fascination of all the missions. I grew up not far from where Grumman built the lunar module. So I keep an eye on what's going on with NASA with the projects. I checked on the blog for OSIRIS-REx the other day, and I want to offer congratulations to you and your team for exceeding the goal. The original goal was 60 grams, and so far it says you've collected 70, with a caveat that they haven't been able to really take apart the tag SEM. There's a problem that two of the 35 fasteners can't be removed with the way it is right now. So I'm wondering if you can elaborate a little bit more on that. I know they're trying to figure out another way into it to obviously preserve the samples. And I don't know if you can say if you have had any guesstimates as to what the total might be, because I read this and it sounds to me like, well, maybe the thing's just too damn full to be able to get everything out.
So first of all, we already have figured out another way to get material out. A lot of that 70 grams came from inside. Cool. So, we announced how we did it. They discovered they could push. There's a Mylar flap that was basically, it let things in but didn't let things out when you collected. And they could push it down and remove some of that. A lot of that 70 grams was removed that way. So it's already been removed by an alternate method. There's no public estimate of how much material is in there. What I will say about the whole process is that we do things that one of the hallmarks of NASA and of this project in particular is you don't rush. You figure out how to do things, you rehearse them, you practice, and then you try to do it. And so when the way we had devised to do this didn't work, what you will see now is a deliberate process where we figure out how to do it, we practice doing it, and then we do it. And it's going to take a little time. I can't give you an estimate of how long that will take, but you characterized it as a problem. It's not a problem. It's just one of the million things that happens in a space mission where you're trying to do something that's never been done before. And so you expect to have things like this happen along the way. They happened at the asteroid, and this happened here, and you get past them, and the team is amazing. So the Curation team is amazing, and the science team is amazing, as was the engineering team. And so it's a great project, and they'll figure this out and move ahead. But only once they know how to do it.
Right. Great. Thanks.
Well, Ceres is the next subject, and I'm actually going to be able to introduce the question asker, Jesse. Jesse is one of our international bolide crew members. He is in Australia, and he is a science communicator at a planetarium, and he absolutely loves working with meteorites in education. So this is the planetarium that he works at. And I think is a great ambassador for them. Here's some old guy he found on the street. I'm not exactly sure who that is. But here's a video from Jesse.
G'day, Dr. Grossman. Thanks for taking time to answer our questions. My name's Jesse. I'm a science communicator from Brisbane, Australia, and I love using meteorites for my daily interactions with visitors at the museum and planetarium that I work at. And often, after handing out pieces of Vesta to hold, there'll be some pretty switched-on space nerd kids that will ask me if I have a piece of Ceres. And that's what my question's about. Where are all the pieces from Ceres? Why don't we have them? Are there some different leading theories for that you could go over and give us the most up-to-date knowledge on? And is it possible that there maybe could be meteorites from Ceres as we learn more about it that we'll be able to identify? Thanks.
So I will say this is not my field of expertise, but Vesta's got something that Ceres doesn't have. When you look at it, Ceres is what shape? It's a nice sphere. Ceres is pretty much intact. Vesta's got a big honking crater gouged out, or two of them, out of its one of its poles, and so it's pretty clear that there's a mechanism for getting stuff out of Vesta, those big craters, and then there's a whole family of asteroids that looks like it is derived from some of that material, the Vestoids, and these have a mechanism for getting into resonances that can deliver stuff into the inner solar system from the asteroid, well, further into the solar system from the asteroid belt. So Vesta's got something going for it to deliver us samples that Ceres doesn't have. Ceres doesn't have half of its bottom missing. So whether there is anything from Ceres, some people have hypothesized that certain kinds of meteorites might be from there. It's dark. It's probably related to carbonaceous material, but there is no definitive way, a link of any meteorites to Ceres. It doesn't mean there aren't any, but there's certainly that big reason why there might be a lot more meteorites from Vesta than from Ceres.
Thank you. We're going back to Matt, and he has a question about Orgay, and I believe.
Yeah, I was just wondering, do they consider this from a comet or an asteroid?
Well, I don't know who they is.
I do know.
There's been a lot of speculation about the relationship between comets and asteroids. There's a lot of open questions here. They're not identical, but is there a continuum? Is a good question. There's been a lot more evidence recently. There's a major, I guess you could call it a theory now, about how carbonaceous chondrites might have originated beyond the orbit of Jupiter, explaining differences in the isotopic compositions of different kinds of meteorites. And maybe they're coming from farther out. Maybe they're coming out from beyond where the snow line was in the protoplanetary disk, and where there might have been more ice. There are also asteroids that have tails. There are active asteroids. So they're shedding volatiles in some fashion. So we don't know yet what all these relationships are. We've only, as far as sample returns going, we now have Hayabusa 2 and OSIRIS-REx that are bringing back material from these carbonaceous asteroids. So we have a chance to start linking the geology to what we see in the sample, the observed geology from the spacecraft. Maybe we'll learn more about what kind of bodies they were and whether there's a link between them and bodies that might be called comets. We don't know. It's a really cool question, and I think we're going to advance it with OSIRIS-REx and with Hayabusa 2. So we'll see. But are they linked to comets? I don't think there's ever been the meteorites that have known orbits. None of them are comets, or Oort cloud comets, or things coming from the outer solar system. Some of them have comet-like orbits, but they were Jupiter family comet-like orbits. So those cross the asteroid belt. So I think there's a lot we don't know.
Okay.
So that's an open question.
Thanks.
But there are small bodies all through the solar system, right? They're in the asteroid belt. They're between Jupiter and Saturn. They're the Trojans around Saturn, which we're visiting with Lucy, or around Jupiter. That's going to be cool to learn more about them. People hypothesize they may come from further out in the solar system. There are small bodies all the way out to the Kuiper belt and beyond. So there may be a big continuum of stuff out there.
Very cool. Thank you.
Before we move to the next topic, can we fit in 2 questions?
Absolutely.
Okay. I wanted to fit these in before we jump to Osiris, but I'm going to let both of the question askers introduce themselves. But the first person we have a question from is Mr. Dustin Dickens, who is also celebrating his birthday today. Dustin, are you there?
Yeah. Hi. Thanks. Hi, Jeff.
Hello.
Nice to virtually meet you. I was just wondering, kind of hailing back to some previous questions, when did the idea of the dense collection area sort of did it pop up out of sheer necessity, or did someone sort of see it coming, and just how did the DCA evolve?
Well, I think you'll find its roots in Antarctica. When meteorites started being found in large numbers in Antarctica, they started getting named for nearby geographic features. First it was the Japanese areas, Yamato and Atsuka, and Allen Hills early on. And as we expanded and started finding concentrations of meteorites in more places in Antarctica, the number grew. I think it's over 50 now, different regions. These are DCAs in every sense. They get numbers along with a prefix. Some of them didn't have all that well-defined boundaries, but the field teams seem to know where the boundaries are. But we've defined them since then, just to try to nail down exactly what the confines of that are. And then, you know, the next big event was the discovery of the Nullarbor meteorites, and they actually drew formal DCAs. There were no geographic features to speak of, and they were finding hundreds of meteorites. And so they went, what do we do? And so they gridded. It's not a rectangular grid exactly. It's sort of quasi-rectangular, following rail lines and whatever other roads and other features are out there. That was the first kind of non-Antarctic grid, I think. Maybe also not that different in time were the Roosevelt County and Lee County, New Mexico DCAs, just big concentrations of meteorites found in flat areas without a lot of names. And then everybody started searching deserts, and well, you know the rest of this story. And so we've basically formalized the way they're named and where they are. It's all very organic. They're not the same size everywhere. It sort of fits the need for each area, but we followed it ever since. And now there's quite a few countries. Maybe the last country it's expanded into is Bolivia. I think there were some. So yeah, we'll use them where we need it, wherever there's desert.
Very cool. Thank you. I appreciate that.
Thanks, Jeff. We have another question from Mara Christian Cruz. Are you there? Can you introduce yourself and ask your question?
Hello, Dr. Jeff.
Hello.
I'm Christian, a geologist from the Philippines, and currently working as a science research specialist too at the Mines and Geosciences Bureau, and also an INCA member and part of the team that registered Pongo Meteorite, which is spearheaded by the Cascadia Meteorite Laboratory, thanks to Daniel and Dr. Melinda. Pongo Meteorite is the most recent and well-documented hammerfall in the Philippines. And right after its fall, we coordinated immediately to our concerned government agencies here in the Philippines for legal exportation of to Cascadia Meteorite Laboratory in US for registration to the Meteorite Bulletin. And meteorites are considered as cultural property here in the Philippines. So my question is, since you're a member of the Meteorite Nomenclature Committee, my question is, how does the NOMCOM consider or deal with the legality of meteorites, especially those that are initially exported from the countries that govern them with laws and consider them as important cultural properties? That's all.
Yeah, it's a very difficult question, and you know, we're basically, the Meteoritical Society is a scientific organization, and our primary concern is to make sure that there's no ambiguity about meteorites, that when there's a meteorite should have a name, and that name should be associated with a certain material, and that's really what we want to make sure happens for every meteorite. There are meteorites coming from all around the world. Many countries have problems with export and with cultural property and everything. And we basically are faced with the situation where we can either be a legal group where we have requirements for export papers and all this stuff, or we can be a scientific group. And we don't have the resources to be a police force or to try to look at that. It's a very difficult thing. There's some cases that are pretty obvious, where we obviously don't want to get mixed up with it, especially when, well, I don't want to try to speculate on details, but we try to stay away as best we can and just stick to naming the meteorites. In a certain way, publishing the name of the meteorite and who collected it and where will help any country that thinks something wrong has happened, because they will have the information about who collected it and how it happened. So, you know, there's no good answer. We don't want to encourage smuggling and cultural theft, but on the other hand, we don't have the resources to really do anything about it and to check on it. So it's a hard situation. We try to stick to our own ethics. We you know, if we won't participate in something, members won't participate in something if they think it's wrong, and if they think they ethically cannot. But it's really tough, and so we just try to get knowledge out there. That's how we address it. And you know, it's not perfect, but we do the best we can.
Because I'm asking that because our commission for culture and the arts is tapping me to help them in crafting guidelines regarding the exportation of these meteorites. So I think your answer will be considered in those guidelines, sir. Thank you.
Okay.
Thank you. We do have one more question before we move on, and I just wanted to make sure we got it in because Daniel does have to leave. Daniel Shake, I know you're probably familiar with that name, Jeff. He has a question regarding lunars. So Daniel?
Hi, Jeff. We've met once in person at LPSC back in 2018, and we've had numerous email exchanges. And I just had one question for you. So regarding the existing nomenclature that we have for lunars, so Ryan Ziegler a few months ago at MetSoc gave a presentation on trying to expand or sort of change the way that the existing lunar nomenclature is, going from feldspathic britches to something a little more sort of advanced than that. I was wondering, are there any discussions that have been ongoing in terms of sort of changing the way lunar meteorite nomenclature is? And if so, what sort of ideas have been proposed?
So the history here is that, especially me, I have pointed out to Ryan, who's the curator of the Apollo collection at NASA JSC, that there's this mismatch between the way Apollo rocks were classified and the nomenclature scheme they used, and the one that meteorite classifiers are using. The two systems are very different, and they serve different purposes, but they can't be compared. And so I said, why don't we put together a consortium of classifiers and others who are interested and try to come up with a scheme by which both can be classified consistently. And so the community then took off with that. And I know there has been a consortium of some kind that's formed, and they're planning on publishing something about a recommended new system. But it, like we were talking about before, it's going to have to be adopted. And to me, it has to be adopted both by the Apollo collection and by meteorite classifiers. Hopefully, it'll be progress and not more chaos, but it's an attempt to unify the two kinds. They're both moon, they're all moon rocks, right? They should be able to be classified the same way. And so that was the point of that. And it's just in its stages where they're gonna have to publish it, and then we're gonna have to see what the community wants to do. So you want to follow up?
Well, that's thank you for your answer, and always happy to continue submitting more lunars. So we'll probably have more email exchanges. Thanks so much.
Okay, yeah, that's a case where the Nomenclature Committee said, "Hey, community, this is not working very well. Do something about it." So we're not always passive, but we're not going to adopt what they do until the community adopts it.
Stephen O'Meara is not with us. Just so you know, he's the finder of main mass of Barnstable, only the second meteorite ever found in Massachusetts. It was a cold find, and he absolutely loves being a detectionist.
I remember this one.
Every year he well, not every year, but most years he tries to bring it to Tucson so we can all take pictures of it together. So yeah, it's kind of a cool thing. He had a question because he's a cold find hunter. He was asking about are glacial moraines deposits good locations to search for meteorites?
That's a really cool question. You would think they wouldn't be, right? The glaciers are carrying all kinds of rocks and depositing them in these features when they retreat or as they advance. I'm not sure of all the mechanics of glaciology, but moraines I've walked moraines. They're just huge rock piles. So, I mean, they do pick up everything along the way, but there doesn't seem to be a mechanism that I know of where they would concentrate meteorites and separate, and concentrate them relative to rocks. Yet there we go in Antarctica, where one of the places where they go every year, they've gone many times. There's a moraine called Meteorite Moraine, and guess what? It's full of meteorites. So that moraine is a great place to search for meteorites, but I'm not sure they know why. So that's a question for Ralph Harvey and Jim Carner and the other people who search that area, and I'm sure they have ideas about why that moraine is a great place to search. There aren't that many meteorites from the rest of the world found in glacial moraines. Okay. And some of them have turned out to be not real.
Even when something's not in your wheelhouse, you know someone who knows something, but I guarantee you this next subject is right in your wheelhouse. Chondrules. So
that was my dissertation.
We're going to call on Bolide crew member Pat to introduce himself and then ask his probably subtyping question if I know him.
Yes, thank you very much for spending your time with us. I know your time is extremely valuable, and you are one of the grand old men in this community. So I'm a co-classifier. I've been working with Daniel Shake. He has graciously allowed me to do some of the science in my own private lab here at home, Meteoritics Lab. I'm a retired engineer, but my passion has been for meteorites for 35 or more years. One of the things in my lab, I just got a wire saw and been taking that journey and really enjoying it so far. I have read and reread and reread the onset of metamorphosis in OCs and carbonaceous chondrules. There's a few of the microscopes in my home lab. So can you tell us in lay person's terms how you came up with the chromium oxide and the ferroin-olivine and how it migrates and how we use those to state the very, very first part of this metamorphosis. How did that come about as being the signpost for 3.0, 0.05, et cetera, and as well as the details of chromium oxide and the ferroin-olivine, especially figure 15 and amount of CR02 or CR203 and its standard deviation?
Yeah, it was kind of a serendipitous discovery, the chromium part. I'm not even sure I remember how I noticed it. But what we were noticing was the same thing as what happened in 1980 when we were subtyping the type 3s to the first decimal place, which is that there was a lot of variation. Semarcona, which is a meteorite that I studied for my dissertation, was obviously much more primitive in many ways than Krimka and Bishenpour, which were traditionally the two meteorites that seem most like it. And something was different. And so we started looking, or I started looking for other properties that went with it. And I don't remember even how I stumbled on the chromium. It was just an observation that, hey, something's going on here. And then I started studying them systematically and figured out what was going on here. what you may not know is you can tell the difference between a 3.0, 3.05, 3.1, and 3.15 yourself with just an optical microscope and a thin section. You can see the chromium X solution with your own eyes. All you got to do is look at big olivine grains and stop down the aperture. So you're seeing lots of what are the lines? It's been a long time since I took my petrology course, but you see in high contrast all the cracks and other subtle features in these grains, and the X solution stands out. You can see it with your naked eye under a microscope. Well, not naked eye, with your lensed eye under a microscope. So you can actually see the difference. And you can look at the sulfides and oxides too and see the difference between these types once you train your eye to do it. So that's pretty cool. And I think most professionals don't understand that you can do this.
Wow.
They'll do the chromium work diligently and get the quantitative answer, but you can actually see it.
Cool. Well, my holy grail is to classify 3.00. I have a little over 50 kilos of candidates in my home lab that will be in the Met Bowl soon, I hope.
Yeah, these are great. You know, the trick is Semarcona is a fall, so it not only is like that, but it preserves a lot of its primary features.
Right.
And it's
Thank
got
you.
a very fine-grained porous matrix, which is very susceptible to weathering.
Cool.
I'm going to move along to Jeremy. Is Jeremy with us? I have a question.
Thank you for being with us, and I'm a new member here. I recently discovered over a sabbatical that I had that one of my happy places is in a strewn field, and so I'm very happy there. I'm also happy reviewing content like this. The fact that you are here with us and that Topher can make this available to everyone else, it's a big deal. So my question is, what is currently at the cutting edge of chondrule research, and what future innovations do you hope occur?
Wow, that's a tough one. I mean, we learn more and more about chondrules. We learn about, you know, their detailed isotopic compositions, first at the whole chondrule level, and then at the grain by grain level, and even at the atomic level. And the cutting edge is trying to take those things we learn and couple them with astrophysical modeling to try to figure out realistic conditions that they could have formed under, or to turn it around to constrain what the astrophysical conditions were in the protoplanetary disk where they were forming. It's a tough problem. It's one of the oldest problems in meteoritics, and you know the answer is not well known yet. So I don't know what I could hope for here, other than continued research to try to figure this out. Maybe our exploration of the solar system will help here as we start learning more and more about where the chondrule bearing bodies actually are in the solar system, and where they might have formed. But it's tough. This is a hard problem. You know, there's evidence that there was chondrule-like material in comets. We found that in Build 2 when we did the Stardust mission. And so there's mixing in the solar system, and it's a tough problem to figure out how it all works. So
well, thank you so much. Yeah, appreciate
I'm sure you. Not the answer you hope for. I hope it's solved in the next 50 years.
Well, just the fact that you're getting into origins and everything else, it points to how exciting our hobby and also your work is. So thank you so much.
It's my pleasure to introduce Marissa. Marissa has some questions, and she is the resident thin section artist of our group. She's also the secretary of the IMCA. Marissa, are you with us?
Yes, I'm here.
Introduce yourself more. I'm very sorry. Introduce yourself more if you want.
Yeah, sure. So Hello, Jeff. I'm Marissa. I've been collecting meteorites for about 12 years now. I got into astronomy, and then a year later, meteorites followed. Like a lot of people, I didn't know you could own and buy meteorites. I thought that was something only the museums could have. And then I got a meteorite in the mail as a promotional gift, and from there I knew you could buy them, and I started collecting them. Since then, I've gone meteorite hunting and successfully found some meteorites, and I did all that in my power wheelchair. So as far as the meteorite community knows, I'm the first physically disabled person to go meteorite hunting and successfully find some. I'm very into thin section photography, and my favorite meteorites to get are carbonaceous meteorites. So my question for you is, can there be or should there be an updated chondrule type identification chart by optical observation? Oftentimes I find chondrules that are like a mixture of two or more chondrule types, and I can't identify the chondrule type, or they've been so melted that I can't name the type.
Welcome to the world of chondrules. One of the things that I discovered when I was studying them way back was that as soon as you sat down with somebody else at a microscope and said, okay, let's look at and you name your favorite type of chondrule, and you just search and you search and you say, well, that's not really one, and that's not really one. And then you'd stop and you go, well, what's that? And the other person would go, I don't know. Let's keep looking. So our eyes are drawn to the ones that are easy to describe, like barred chondrules. You got one there on the left. You know, everybody recognizes that, except when the bars go in 7 different directions and it's porphyritic on one half. You know, there's a lot of variation, and professionals don't do any better than you do. You know, they will just see, or is it more than 50% olivine, or is it more than 90% olivine? Then it's a porphyritic olivine, like that classic one you have on the number 2 on the top. But you know, you start getting to other things like the ones on the right, and you know, what is that? Is that a porphyritic olivine chondrule number 3? It's got a barred thing in it. You know, so there's all kinds of variation. And so when you start making a table with the classic types, you'll find that, well, yeah, that describes 10% of the chondrules. Now, what about the other 90%? Well, it's this grungy thing I show over here. I don't know what that is. That's the way it is with chondrules. Whatever process formed them was capable of forming a lot of variation. Maybe the starting materials were varied. Maybe the conditions were varied. The cooling rate might have varied. There's all kinds of things. Maybe it encountered dust when it was cooling. Maybe it didn't. There's so many things that can happen, and the text and a wide variety of textures form. So, you know, you can make a chart like this, but most of what you see in the meteorite you're still going to say, well, what's that? That's just the way it is. So this is a good start. I don't know about poikilotic pyroxene. I guess I've never heard that as a type, but it certainly describes the texture of some of those pyroxenes I see in there.
We are always on the lookout for new things like this. We did not create this. This is floating around some of the good Facebook groups. So I would love to better what is out there with Marissa's photography, and maybe leaning on you once in a while. That'd be fantastic.
Go back to that thing again.
Yep.
The second one on the top row, those are the kind of chondrules where you can see the exsolution of chromium if it's below petrologic types, for those who want to look. Those are classic type 1 FeO-rich chondrules.
I think that actually leads directly into what Pat's question is. Pat, you're talking about low subtyping, aren't you? And what to look for?
Dr. Grossman, I'm buying rocks, looking at rocks, looking at from the outside with a reflector cross polarized light to look through the desert varnish. This one is a slice, but I found a few things from looking at slices that I own of classified meteorites that are 3.00, 3.05, etc. And of course, very fine, small rims of matrix, black, very little matrix. We think this one is a 3.15. We've got data that we're going to submit with this one. But things like AOAs in ordinary chondrites, CAIs in ordinary chondrites, carbonaceous inclusions in ordinary chondrites, and from the other slide, chondrules with holes that show, incomplete melting or maybe even relic grains. Are any of those signposts for searching for good candidates for 3.XX?
I don't think so. The textural clues of that is get a polished section, really good polished section, and look at the opaque phases. You'll find very complex assemblages of metal, sulfides, and oxides, and oxysulfides, and all kinds of complex things. Right. That's a hallmark of a lot of these low type ones. Is the oxides. Now you got to be careful. This thing is really weathered. And
yes, so sorry, this is a bad slice and a bad photo.
So there's going to be a lot of oxides in here that are terrestrial. So so you got to be careful. A lot of the metal in the primary phases may be gone, but the opaques are something you can look at. The matrix should be black and opaque. Sometimes you see little tiny specks of sulfide in it. So it's mostly in these delicate parts of the meteorite that you see it. The matrix, the opaque assemblages, and the olivine in the type 2 chondrules.
Okay, one thing I've just started doing is dry cutting on the wire saw, and that allows me to look at the troilites without any of the limonite corrosion that we saw in that photo.
Yeah, you'd want to get it really well polished, mirror polish.
Right. Okay.
We are going to go to Scott, who has another question for you.
So, Jeff, we have to know, between your professional career and work on the Met Bowl, you've studied more chondrites than almost anyone. What chondrite most sparks joy for you, and do you have a favorite chondrule?
Well, I don't know about a favorite well, I have, maybe I do. This is all from way back. My favorite chondrite, it has to be Samarcona because I discovered how primitive it was. And it's a meteorite collectors don't have because the bulk of it was in India in a museum, and then the rest, the U.S. part, went to the Smithsonian. I don't think it's ever been traded. So it's a gorgeous meteorite, and it has to be my favorite meteorite because it's the one I studied more than any other one. Beautiful thing. My favorite chondrule is probably one from a paper I wrote in like 1982, where it was an ovoid chondrule that had a metal blob at both ends, and it had clearly been spinning. Except that when you spin, metal will go to the middle, but something was going on like that. So the metal would go out, and bubbles would go to the middle. So that was a beautiful example of a chondrule in the process of fissioning. So I thought that was pretty cool. Maybe that's my favorite chondrule. But I don't know, I've probably seen 10 million chondrules.
I was going to say, how do you narrow it down out of the 10 million? Well, Jeff has another question for you.
In your opinion, Jeff, what's the holy grail discovery in meteoritics and planetary science you hope to participate in, or you hope to see in your lifetime?
That's a hard. Look, everybody wants, and you're not going to get it from chondrites, but everybody wants to understand the origin of life.
Right.
And so, it's going to be. It's in planetary science. That is one of the holy grails. Clearly, is to figure out either how life formed, or whether there is other life or was other life in the solar system. It's got to be one of them to really better understand the early solar system and how it worked. I guess is another one. But it's a hard question. You know, none of these are really a holy grail. You know, we're trying to build a big picture of the solar system, trying to understand it, and we have pieces all over the place. We don't know how they all fit together, and the more we learn, the more we can fit the pieces together and get a better picture of what it actually was. We're reconstructing something that doesn't exist anymore and hasn't existed for 4.5 billion years. And so, you know, it may not be a massive discovery about the early solar system. It may be just the accumulated knowledge from missions and from meteorites and from everything else that lets us just form a better and better picture of what happened and how the solar system formed and how planets form and all the rest. So I'm not sure I want, you know, beside the big questions like the origin of life, I'm not sure I want to put one thing out there. It's everything.
No, fair. Very good.
A little bit of everything everywhere. For our viewers, if you guys have questions that you'd like us to address, please drop them in the chat and in the comments below. We definitely appreciate it. I'm not going to kick you out of here, but we would definitely want to show our appreciation for your time. You're generously giving us your time and answering questions. I haven't seen a whole lot of your lectures or interview sessions like this online, so this is truly special, and we thank you very much for sharing your time with us.
You asked me at the beginning why I did this. It's because you asked.
It's because I asked.
Yeah, my wife was bold enough to ask. I had no idea you'd know who we were, what we were doing, and you would laugh at us backyard scientists.
I didn't know exactly who you were. I know you better now, but I know what you do. So because like you said, I see it all on the Nomenclature Committee.
Yeah.
You know, collectors are always part of the picture and a fun part of the story often.
I'm not sure if you are anxious to take off, but I'm sure if you stick around, there's going to be some ad hoc questions being thrown at you. I just don't want to overwhelm you. It's been an hour and a half to 2 hours already.
I could take a few more, but it's getting late here, so probably not too much longer.
All right. This is when I step back from the controls and all chaos ensues.